Okay, so today's focus, we're going to continue with our comparison of functions. Okay, so we learned about what a function is. We started to talk about finding the initial value, finding the rate of change. The next layer is that we can compare. And what you'll see is you'll be given two functions similar to this scenario. One is in a graph, one is just explained. And then they're going to ask to compare things. So if you were going to compare things, how would you compare them? Like if you were going to compare like my height to somebody else's height, what would you say? Okay, you use the numbers. You say maybe I'm taller than Jamie, or Jamie's shorter than me, or my height is double her height. You know, whatever it could be. Not that those are true, but you know, those are different ways you can compare. So as we go through these scenarios, think about ways to compare, and primarily we're going to focus on comparing our rates of change in our initial value. Okay, so here's the scenario. A biologist studied the growth of two different trees over a 5-year period. At the beginning of the study, he measured each tree's diameter. If I'm looking at something round, how do I measure the diameter? Diameter.
Radius times pi?
Not radius times pi.
Radius times 2?
It's 2 of the radius. So how do I measure the diameter of, like, let's say a tree trunk? Let's say I cut the tree and I'm looking at like the round part of the trunk. How do I measure that?
Go from one side to the other.
Yeah, just from one side to the other, right through the middle. The radius is from the middle of the circle to the outside. 2 of them would really just be straight across your circle. So the biologist is going to measure that. He took the measurements and here's what he found. The red maple in the study had a starting diameter of 4 inches. The diameter grew at an average rate of 0.3 inches per year. The graph on the right shows the silver maple. So we're going to figure out which function has a greater rate of change. Okay, what is it going to mean in this scenario? What's the rate of change going to represent here in words? Because we're talking about trees. What's the rate of change going to represent? Which tree does what?
How much it grows?
How much it grows, and if we're talking about the rate, it's which tree is going to grow faster. Which one's growing faster? So that's what we're going to figure out. You may be able to see it already. Okay, so we can use a table to fill in some information. Okay, so for the red maple, how do I fill in the diameter here? We have 0 years, 1 year, 2 year, 3 year, 4 years, 5 years. How do I fill this in with the values? Like what do we know? What can we add in? Erica.
For 0 years, it's 0 inches.
Is the diameter 0 inches at 0 years?
It's 4.
How do I know it's 4?
Because that's how the maple tree started.
So it says at the beginning of the study, you're not always going to see them use the number 0. Sometimes they're going to say at the beginning of the study, or when we started the job, or that day's production, when it began. So that would be your initial value. The initial value here was 4 inches. So it was like an itty-bitty baby tree when the study started. You're not going to start it from it being a seed. They started when the tree was already like kind of grown. Okay. And then what happened? What happened in year 1? What was the diameter? Maggie. 4.3. How did Maggie get 4.3?
Because she added 4 inches, which was what it already had at 0 years, and then she added 0.3, which was what it's growing at every year.
Yeah, we know that it grows this much every year, so she added that into the previous year's diameter. So what's year 2? 4.6. Year 3? 4.9. Year 4? 5.2 and 5. 5.5. Perfect. Okay. So now, can we use the values in this table to graph? Can we graph this? How do I graph this if I have the table? What do I already have if I have a table? I have the coordinates. They're right here. What should I put on my x-axis? The diameter or the years?
The years.
Okay, let's do our years, because every year, every time a year increases, something happens. Okay, so we'll label this 1, 2, 3, 4, 5, and 6. How do you want to label the y-axis? Do you want to do like 1, 2, 3, 4, 5? Do you want to do, what do you think?
4.4, 4.1, 4.2 on
all the way to like.
Okay, so we could try to do it like real small. Another option you have here is if you look at the original table, the original graph, like for the silver maple, we're now graphing the red maple. Sometimes when you're comparing, you want to do what I call is comparing apples to apples. So if I had a graph where the numbers were like 4.1, 4.2, 4.3, then the graphs may not look the same. So you may want to label it the way the other graph is labeled. And the only reason we're going to do that, you have your choice of graphing, the reason we're going to do that is because when you see them later, they're compared this way. Because it's much easier to tell which one is growing faster. So what am I going to plot? What are my points on this graph?
4
And what?
at the 0.
Okay, so explain that. Go a little bit further with that.
So like since you're not moving to the right any, so you just go up 4.
Okay, so this is my initial value. Why is it my initial value?
Because it's what you started with at 0 years.
Okay, so it's what I started with at 0 years. And what we want to remember from that, this is a big thing, this is the trick here. It's not just where the situation started, it's at 0 years. You may be given a scenario where they start by telling you in year 2, this is what they measured. So you may have to go back and figure out where it really began. What's another point on this graph? I'm going to make this a little smaller so that it doesn't look as like obnoxious. What's another point on this graph? 4.3. Where's my x value at a y of 4.3? When x is 1, y is 4.3. What's another value? When x is 2, y is 4.6. Can I keep going or should I just draw my line here? Could I do that?
Yeah.
How many points do I need to draw a line? I really only need 2. If you're concerned that your line isn't going to be straight, if you know you need to find where does this line meet when x is 10, then you may want to keep going. Otherwise, like if you just do 2 points and draw a line, your line may not be straight. But for this scenario, we're good here. I mean, our line looks pretty realistic. Okay, what are the options? When we talk, I'm going to pull all these down. When we talk about rate of change, doesn't only have to be a tree. What are other scenarios where we may be talking about the growth of something? Any scenario. Money, okay, maybe I'm saving more money, so my bank account is growing. What if I'm spending money? What's happening to my bank account? It's going down. Good, what else can be happening? What other things talk about growth? Height, yeah, maybe every year someone's growing an inch. Do you think that something like that, height, or even money, do people always grow the same exact amount over the same amount of time? No, so that's not always constant, right? Our functions here are not always constant or linear, but right now we focus on linear. Okay, can I compare any 2 rates? So like that tree's growing this fast, that tree's growing this fast. Can I compare anything? Who makes more money? The person who makes $5 per minute or the person that makes $6 per hour? How do you know? Because like when I see that, a lot of students in the other class said the 6, because 6 is bigger than 5. What's the problem by saying the 6?
For an hour, you're only being paid 6. I have it on my exam.
Who can help Giselle explain? Because you're trying to explain exactly what you want to say.
You earn $5 per minute, rather than 6 per hour.
So this is the key here. Oh, I don't know why I just circled the word work. Sorry. So it's minutes compared to hours. If I'm going to compare things, what do I need to guarantee before I start comparing the numbers?
They have the same label.
That they're labels, or we can even refer to them as units, that they're in their same measurement. You can't just look at it and say, hey, 6 is more than 5, so we're good. Because that person makes $5 a minute. So how much do they make in an hour? 300. They make 300.
Please pardon the interruption. Leo, the custodian, can you please report to rooms 19, 20, and 21 area as soon as possible? Leo, the custodian, please report to the area of rooms 19, 20, and 21
Okay, so the silver maple and the red
with a mop.
So the silver maple and the red maple are there. We were given the silver silver maple, and we just graphed the red maple. So this is just like the actual picture of it. How do I find the initial value on the graph? Where is it? Shirley.
On the y-axis.
On the y-axis. And why is it on the y-axis? It's not just where this starts. There's one more thing that you need to know about it.
It's on the y-axis because you're not moving to the right any. So it starts at 0. So you're not moving.
What is 0 there?
The origin.
What value is 0 at that y-axis? What coordinate is 0 at the y-axis? Is it x or y?
Y. I mean, it's both. You never both because like it's a 0 for the y and a 0 for the x.
What's this coordinate right here? What's that coordinate? 0, 3. And what's this coordinate? 0, 4. So our initial value is the place on the graph where what? It is the y-intercept, but why? What's the value that matters? Yes, but how do I know? What if my graph started, what if I had a graph that looked like this? What's my initial value? It's not 8. Why is it not 8?
It also starts at the 1.
Because what?
It also starts at
Because this coordinate starts at an x of 1 and 8. Where would I have to go to find the initial value of my new function?
the y-axis.
To the y-axis, because what value matters? It's not when x is 1, it's when x is what? 0. X has to be 0 for your initial value. And what do these initial values represent? Not my new function, the trees. What does the initial value represent here?
What was the diameter when the tree first started?
Yeah, when we first started the study, how wide were the diameters? Like how big were the trees? Perfect. How do these lines move? Just by looking at them. How are they moving?
They're moving up, meaning they increase.
They're moving up, meaning the lines are increasing. Why are the lines increasing here? Not a math question, just a world question.
Because trees don't like grow down, they grow.
Yeah, your tree's not going to grow down, right? It's not shrinking. The tree is growing. So you're going to measure that increase or that growth. Are all functions growing up? No, you can grow down, meaning like decreasing bank account. Maybe you have like gallons of gas in your car and you're using them, so the gallons are going down. Right? So our rate of change is found using the vertical change, which is our change in y, compared to our change in x, our horizontal change. What else is our change in y compared to change in x? We've talked about that. Your change in y compared to your change in x. When else has that come up? Say again? Our slope. Our rate of change is the slope. The difference is, it's our slope when we're talking about just a graph. If we're talking about a scenario here, hey, the tree is growing 0.3 inches a year. That's your rate of change. That's the change every year, or it's the rate. So what is the rate of change for our red maple? How much is it growing per year? That's the one we created. We created that graph. What's our rate of change? How much is the one that we created, the table, and then the graph, how much did that grow per year? 0.3, yeah. 0.3 for every 1 year. And how about our silver maple? Looking at this green graph here, how much is it growing every year? Lydia? 3 inches. How do you say 3 inches? How do we find it? Because right now you have to find from a graph the rate of change, or we could also call it the slope. How would you find the slope from points on a line?
Rise over run.
Okay, so where can I begin? Do I need points?
Yes.
Yeah, okay, so which one do you want to start with?
You can start with 3. Is that 3?
So this is my y-intercept, because it's crossing my y-axis. What's the coordinate there?
0, 3.
0 and 3. Which other point do you want to use? What is another idea for another point we can use that we can easily see how we're moving up and how we're moving over? Giselle.
5. No, wait.
Yeah.
5. 5 and 2? 2 and 5?
2 and
No.
what number is that?
4.
2 and 4. Okay. So how did we go up and over? How much did we move? For every 1 year, how much are we growing? So from year 0 to year 2, how many inches did we grow? How many inches did we grow over those 2 years? If we went from a Y of 3 to a Y of 4, how many inches? 1 inch. So we did 1 inch every 2 years. So how much did we do in just 1 year? Half an inch. Okay, so you can say 0.5. And again, what did we do? We took the coordinates that we see. We could have used this other one because here, that would have been 1 and 3.5, a little tough to see. I love, Giselle, that you went right to this coordinate that you clearly knew was an x of 2 and a y of 4. Great. So now we know that our growth for the silver maple is 0.5. So what do the rates of change represent? We have 0.5 and 0.3. What do those mean in context?
Is that the slope?
That is the slope. And what does it mean in terms of the trees? Be more specific. So that is the slope. But what does that mean? So like for the silver maple, what does 0.5 mean?
Every year it grows.
Every year my diameter is increasing 0.5 inches. And how about the red maple? Every year what's happening? Our tree's getting bigger, but how much bigger? 0.3 inches. So which one has the greater rate of change? Which function has a greater rate of change? Why the silver maple?
Because it's growing more than the red.
Yeah, it's growing more than the red maple. Every year that passes, my silver maple is growing half an inch. My red maple is only really growing like 1/3 of an inch or 3/10 of an inch. So yes, my silver maple is going to grow. If you're just looking at the graph, how do you know the silver maple is growing at a greater rate? What's happening with the line?
It's more steep.
It's steeper. Yeah, it's a little tough to see because both lines are relatively flat. But if you really looked at those two lines over time, the silver maple is growing at a much greater rate. We already talked about that. Okay, so you're going to, I know this is a little odd because normally we like practice before we do our DOL, which is okay. In an effort to save a little bit of time, we are going to do our DOL as our practice. Okay, now your DOL doesn't go against your grade. It's really just to see like what we need to spend a little bit more time on. I'm going to give these back though, so that you can do them on the same papers. There's really no reason for you to take a new one. Can you help me hand those out? Thanks. I'm actually going to pause the video.